Welcome to our video. In this video, I will introduce our research titled Ammonia, an approach for deriving project-specific bug patterns, which has been accepted by Journal of Empirical Software Engineering last year. Here is a snapshot of web page of PMD, which is a popular statistical analysis tool. The overview says PMD is a statistical analyzer. It founds common programming flaws like unused variables, empty catch block, and unnecessary object creations. The underlying idea of statistical analysis is there are some commonly occurring bugs across all software products, and such bugs often have identifiable patterns. Therefore, statistical analysis tools employ a set of rules for commonly occurring bugs and scan the target source code. However, we consider there is an issue in current statistical analysis tools. That is, current statistical analysis tools do not contain any specific bug patterns that are part of a particular target software project. So in this research, we try to detect potential bugs by using project-specific bug patterns deriving from commit histories. I will explain why we consider mining commit histories works for deriving project-specific bug patterns. This slide shows a real bug occurred in project Camel, which is included in Apache Software Foundation. This bug has been already fixed by a developer. And this is the patch to fix the bug. The red line is the buggy code, and the green line is the fixed code. This slide shows another bug occurred in the same project. This bug has been already fixed too. And this is the patch to fix the bug. Here we compare the two patches for the different two bugs. We can see that the buggy code and the fixed code in the two patches are very similar to each other. Only the difference between them is variable names in the code. So we can derive this change pattern from the two different bug fixes. In this change pattern, only variable name is normalized. And in this change pattern, some methods defined in this project are invoked like this. So which means this pattern is a project-specific one. As shown in this example, we can derive project-specific bug patterns by mining commit histories. Next, I will explain the procedure of our approach. For a given project, our approach extracts changes from every consecutive pair of revisions. Then our approach make a pattern from a set of changes whose before change code and after change code are the same. Our approach also counts how many times each pattern occurred in the commit history, like this. Next, I'll explain how our approach detects buggy code in the latest revision. Our approach checks whether the latest revision includes the left-hand code of this orange change pattern. If it does, our approach recommends the matched code be replaced with the right-hand code. Of course, the same things are done for all the other change patterns. Next, I will talk about evaluating our research. The purpose of this evaluation is examining the ability of our approach to detect potential bugs. We used these for projects included in Apache Software Foundation because these projects assign a unique ID to each bug occurred in the project. And the commit message of bug fix commit includes corresponding bug ID. Thus, we can judge whether each commit is bug fix 1 or not. In this evaluation, we made a pull request based on the detected potential bugs. Now I will explain how we did the experiment. First of all, we detected change patterns whose changes occurred at least once in the bug fix commit. And as a result, we detected a large number of change patterns as shown in this table. And next, in step 2, we extracted change patterns whose right-hand code are the same for all the changes. I will show an example of this extraction. In the left side case, 3 code fragments are changed. The 3 blue code fragments are very similar to each other. And only one of them is changed to the red code, and the other 2 code fragments are changed to the yellow code. This means there are 2 change patterns in the left side case, and their before change code are the same, while the after change code are different. In other words, the 3 blue code fragments are changed in different 2 ways. We do not use change patterns derived from such a case. And in the right side case, 3 code fragments are changed, and they are changed in the same way. In such a case, we use change patterns. We obtained those number of change patterns as a result of step 2. Next, we detected potential bugs by using those change patterns. In this evaluation, we extracted patterns that match only one place in the target code. And then in step 4, we manually investigated whether that matched code is buggy or not. And unfortunately, we couldn't determine whether the matched code is buggy or not for some patterns because we are neither the developers nor expert for the target project. And in step 5, we sent a pull request for the buggy code via GitHub. This slide summarizes 6 pull requests that we made. For example, for Ant, our approach suggested move method invocation outside the loop. And for Camel, our approach suggested to invoke a different method. And those numbers means the ID of pull request that we made. If you are interested in, you can see the detail of the pull request in the GitHub repository of the target project. At this moment, 5 out of the 6 pull requests have been merged. Only one of them was rejected. The reason why the pull request was rejected existed in the code. The code comment just above the matched code says, do not optimize this loop by replacing children.size by a variable, as children can be added dynamically. In investigating whether the matched code is buggy or not, we missed the code fragment. Okay, now I conclude my presentation. In this research, we conducted we proposed an approach to detect project-specific potential bugs, and we detected the tool chains. We developed tool chains for the approach, but due to time limitation, we couldn't introduce them in this presentation. But you can download the tool from this URL. We conducted a developer-involved experiment, and 5 out of the 6 pull requests were merged based on bug-related issues, and 4 out of 5 pull requests were merged based on non-bug-related issues. This means a kind of refactoring. But the latter case, I couldn't explain due to time limitation. If you are interested in, you can download the replication package from this URL. That's all.
Okay, welcome to the Q&A session for paper 2, where we've seen the presentation of the paper, MC paper, Ammonia, an approach for deriving project-specific bug patterns. And we have two of the authors here, Shinpei and Yoshiki. So feel free to post any questions you have in the chat. But for now, I'd like to start with one of my questions. So very nice paper, and very nice that you submitted actually pull requests to these projects and even got many of them accepted. So, I mean, I guess my first question is, are bugs really project specific, or are they more like developer or human specific? Can you comment a little bit about this?
Actually, our technique can detect any kind of bugs that happens in the target project. So, in the title of my paper says project specific, but actually our technique can capture other kind of language specific or developer specific bugs, I think.
So, and we have one question from Leandro, which I guess connects to this. So can you describe a little bit more the technique you use to detect patterns? So you do some kind of normalization or abstraction, I guess.
Okay.
I mean, not too many details, but on a high level.
Yeah. And okay. How to say? Our technique, of course, we use a normalization technique to capture bug patterns that includes different variable names, because the structure of the programs change structure of the program. Change structure is sometimes same, but variable names in the changes are sometimes different. So, but we want to capture such changes in the same change pattern. So we need to normalize the variable names. It's a kind of our techniques, and also we to faster the searching faster the matching speed, we use hashing algorithm, MD5 hashing algorithm, because we want to avoid text matching, because it's sometimes sometimes costly. Yeah.
I see.
Sorry, it is difficult to say the technical details in.
But
maybe. Sorry, yeah, please.
Yeah, but is the technique like line-based, or can you also detect pattern on like more complex changes?
Yes, actually a line-based technique. Our technique is line-based ones. We generate MD5 hash values from each program statement. It means we do not use any other complex technique, for example, abstract syntax tree or program dependency graph. So our technique is very faster than the other existing.
Yeah, that should be very fast. But then what happened? How do you handle if a bug fixing commit is has multiple lines? You just consider each line independently, or?
Our technique, both, of course, and single and multiple line. But in my impression, in multiple bugs, maybe precision is a little getting lower, I think.
Note that although we use statement lines as a unit, but we capture the changes as a chunk, sequence of the lines, change the part, so that we can capture such a multi-line changes.
Yes, so it means if one change is separated in two chunks, our changes cannot capture at this moment. Any other techniques, for example, syntax tree or program dependence graph-based techniques are required to capture such changes.
Okay. Nice. So I have another question, which is, did you investigate if some project-specific patterns from one project could also be useful in one of the other projects? Did you at all look at this?
We found such patterns, but we do not how to say evaluate that. We found,
Okay.
but
Yeah.
and in the paper, the main goal is finding bug fix patterns. But in addition to that, we did a kind of other kind of changes, like I mean refactoring suggestions we did. And such refactoring suggestions are maybe more useful for other project.
Right, and I guess your normalization might need to be even more brutal in a sense, because maybe even if the pattern is similar, maybe the method names will change between projects, right? So yeah, I can see that there are some challenges there, but I also think that there will be developer specific or even human specific bugs that you can also detect if you abstract more, maybe. So I guess an interesting future work possibly.
Yeah, and one thing we need to care is that if we normalize all the names in the programs, it doesn't work better. I mean, variable names, any kind of variable name does not affect the program behavior, but the method names, if this in this code fragment method A is invoked, and in this code fragment method B is invoked, two program statements, two code fragments have different behavior, right? So we can normalize variable names, but we shouldn't normalize method names. So we carefully choose what names we should normalize.
Yeah. Did you do any type of manual comparison between your sort of the patterns that your technique finds and what is in these the normal static analysis tools? Are there some similarities, or are the project specific patterns very different?
We checked many patterns that our tool detected, but in my impression, no overlap between the techniques, our technique and existing SA tools.
Yeah, I guess that's good,
in other words, we could find many patterns which are not be able to detect it by existing static analyzers.
Yeah.
And did you get any type of comments from the developers of these open source projects when you submitted pull requests? What did they comment that this was an automatic tool, or?
Simply have any comment?
Some of the developer mentioned that actually this is the one I missed to implement, so that they were happy to be noticed. But regarding the automated tool, that I'm not sure. Anyway, in general they were happy, but some of the pull requests were rejected because that were not fit in their developing practice or in their process.
I think the number of suggestions from the automated tool should be small, because if many suggestions are provided by the tools, it is very difficult for developers to check all the suggestions, right? Only small suggestions are very good.
Yeah, this is a well-known thing. I've seen it in Sweden, where we applied static analysis tools in industry, that if they give 10,000 alarms, then people will stop. So yeah, it's much more important to be really on point and find the important. Okay, we're coming to the end. We don't want to push the last seconds here, so thank you very much. Interesting paper and interesting approach, and I guess there will be more of this type of work where we adapt the general techniques to specific projects. So thank you a lot, and I hope many of in the audience stay for the next paper. So see you there. Thank you very much.
Thank you very much.
Thank you.